So I actually lead the quantum information and inference group in Warsaw, actually in the same center for quantum optical technologies as Michał was just talking, is leading the lab there. And actually we've been working for the last 2 years how to some kind of adapt things we've learned on quantum metrology to quantum sensors. So what I'll tell you in this 15 minutes is how to tame this kind of challenges the sensors have. But I will really advertise the 3 works that we've done that were in the poster sessions. Unfortunately, I'm speaking after the poster sessions, but I will try to be explicit so you can approach the people that if you are interested. So what are these quantum sensors? There have been plenty of talking during this conference. So what I mean is, for instance, solid-state quantum sensor. These are the ENVI sensors that Dimitri Budker was explaining yesterday. Just remember, we have a diamond in which 1 carbon is replaced by a nitrogen, so we have a vacancy next to it. And this behaves as if it was an artificial atom. What I would like to draw your attention to that you need to pay a lot of time and effort to actually address it, and you need to use some external beams of light to control it. Actually may be different, but my point is they are all pretty similar. If you look at atomic sensors, in particular in magnetometry, we have atoms that are typically in a cell. This is actually from Michał's lab. And we address them by means of laser, and then in essence, they behave in a collective quantum system. Furthermore, we have the optomechanical sensor. Michał just gave you a beautiful detail, so I will not talk much, but here we have the oscillator, which is coupled to cavity. And again, I need to couple it somehow to light such that I can get some information out of it. And the final one is actually Ian Walmsley's talk. If you think of optical interferometers, this is maybe the simplest picture you could draw. Now I'm interested in sensing some kind of path difference between 2 arms. But let me draw your attention, and Michał has mentioned nicely that these 2 systems are actually very similar, or actually equivalent in some sense, because here you need to bear in mind that the mirrors are actually behaving as optomechanical sensors. Okay, I need to speed up, but let me draw your attention that all these sensors have the same behavior, or this kind of two-stage architecture. In a sense, what you like to have, they work as a transducer. This is what the engineer would tell you. Basically, you have a well-isolated quantum system, which you isolate from the surroundings. Here, it's because it's a solid-state system, so this electron is sitting there, and it's well bounded from the rest of the world. Here, your experimentalist is trying hard to put the atoms in a vacuum chamber, either with, for example, noble gas to stop their motion, or is actually using paraffin coating. Here, okay, Michał just showed you, most likely you need to put it to cryogenic temperatures such that phonons are not being excited within the mechanical oscillator. And now you have some kind of external field force of temperature that is affecting this motion. So my point that I'm trying to make now is what is forgotten is actually to penetrate this kind of system, you actually need to put some signal in and out to get this information that you want from the sensor, either it's the field or force or the temperature. But you should remember that the measurements this way is affecting how the sensor is behaving. And this is what is the current challenge. Moreover, if you think of sensor, you should really think of situation in which the parameter some kind of evolves in time. And actually this signal you're going to measure is very noisy, plus it's also a continuous time wave train, right? So my point is that what we've been working so far was a bit too theoretical, because if you open some kind of classical papers on this, people will tell you that, for example, these atoms you can describe as a density matrix. Each of them evolves independently, so it's just a unitary evolution. And then you some kind of measure some POVM, which represents the interaction with light. Okay, it's a very nice theory. It normally relies on the fact that you have many repetitions. So here comes trouble if you have something changing in time. But the point is that it's it's been working for a long time, and we got some interesting results from it. So I need to really super fast summarize them. So the tour de force that you've seen over the talks is the quantum Kramer-Rao bound. Basically, what you calculate is this quantum Fisher information based on the symmetric logarithmic derivative. And importantly, what I want to draw your attention to is, first of all, is this local frequentist estimation. So this kind of framework works only if you repeat your measurement as much as you want. And this is not the case, actually, if you build a sensor. Secondly, this framework some kind of puts you in the setting that it's already optimized over all potential measurements. And now I've just told you that in quantum sensors, this is not the case. I mean, actually, you have a particular measurement that actually affects your dynamics. So this is sneaking things under the carpet. Still, that there are these notions that I want to remind you of, that, for example, in the simple case of magnetic field sensing or optical interferometry, the parameter is a unitary parameter. So this Fisher information becomes just the variance of the Hamiltonian. And you can easily prove that if I have separable states, if my atoms are separable, I'm limited by the standard quantum limit, so it's upper bounded by n. But now, if I use G at Z state, Nun state, the Fisher information scales I can square it, and this is what we refer to as the Heisenberg limit. And now this is an important observation that I cannot quickly convey to you from quantum Fisher information, but I'm happy Lorenzo mentioned it yesterday. You need actually a separate proof to actually realize that to attain this bound, it's enough to consider local measurements. Okay, so this will be important for me in a second. So I've told you all this, and what my aim is in the next 10 minutes and a bit more is to tell you about 3 challenges that we tried to tackle over the last 2 years in my group. First thing, measurements are never perfect. So this is this motivation. There are certain measurements you can do in your lab. So in this abstract framework that I've just showed you, we were able to incorporate the idea that measurements are imperfect. You have some noise on your measurements. And this was the poster in session B. Ying Long is here, but please also have a look at their archive. And this is largely motivated by NV Center, as I will explain. On the other hand, I told you that sensors work continuously in time. So the next kind of system is actually atomic sensors, and there you have a very noisy signal, and out of it you are trying to infer, for example, the field that changes in time. And then while you are measuring the atoms, you are actually squeezing them forces. So you are affecting the evolution. So again, sneak under the carpet this quantum metrology frameworks. And this is really work of Julia Amoros-Bineva, who is here. She had a poster in session A. Please approach her, and this is the archive number. And the last point that I'm not sure if I managed to get, so apologies to Luis and Bartek if I don't get to advertise their work. But basically, you need to work hard to extract the information you want to get from a quantum sensor. In particular, we look at optomechanical sensor. And what Michał has been showing you that he didn't mention, he works in a linear regime. And now the whole, some kind of challenge in quantum sensors, optomechanical sensors, as you ask many people from different labs, people want to go into nonlinear regimes. And then what we are trying to do is we're trying to measure photons that leak out from the cavity, and you get some kind of click patterns. And from these click patterns, you're trying to estimate properties such as the internal frequency of this oscillator or the coupling. So this is this final part. So measurements are not perfect. I'll manage. So basically, why this is an important question. So these NVs, as I told you, they are spin halves, and then they experience some magnetic field that you try to measure. And let's think of them as a simple qubit system. So you have a Bloch pole, and the spin is really a rotating vector that goes under the field, which is B. Now the fact is, what happens in these experiments is you cannot just directly measure your qubit. You cannot do just a projective measurements you want. What is typically done is it's called repetitive readout procedure. So you can transfer the spin of your electron onto the nearby nucleus, which is the nitrogen or carbon, and then this is a Q&D interaction for the experts. So you can measure as much as you want this carbon to get the information about what was the actual spin of the electron. And okay, plots are better than words. So for instance, notice that you would expect the population to go as a cosine function, but measuring photons, actually you get, say, number of clicks. So it's not that obvious that actually this represents this pattern. And what is the problem? The problem is that you are measuring some kind of Poissonian distributions that are shifted depending whether your state was in, okay, it's a qubit, whether it was in 0 and 1. So this is typical to these experiments, and what people typically do, this was the original works of Jelesko and Rachtap. Basically, what experimenters do, they call it the threshold method. They say, oh, let's draw a line in the middle. If I measure photons to the left over 5 seconds, I said it was 0. If I measure to the right, I said it was 1. And note that this is nothing but a bit flip error. So basically, you wanted 0. Okay, I call it 1 and 2, but there is some chance, which are these tails, that actually the qubit was in 1, but I thought it was 0, right? So it's really a classical noise that flips your coin. And sure, our work is very general. Just please ask King Long if you want more details. I give you this motivation from NV centers, but this is just a scheme in which you measure locally a projective measurement, and you have some stochastic maps that rumbles around. So what was the first question that the experimenter asked this, and this is not obvious. Basically, if you take this system and there's no noise, there you could perfectly measure it, then it doesn't matter at which angle you measure the spin. Now, because you have some kind of experimental noise, there is a strong dependence, and we can actually give the value to the experimentalist at which microwave pulse they should apply to get most information about the magnetic field. And okay, our work is general, so we actually prove for the experts that actually if you have any type of POVM that is noisy, actually the imperfect quantum Fisher information is the quantum Fisher information if there was no noise times a constant factor. And this works for critical metrology estimation. This works not just for phase estimation, it works in general. Basically, it means that this factor here, you just give me this stochastic map and I can calculate it for you. Okay, it's not easy, but that's the point. And now we basically answered this long-standing problem. Okay, but I told you about this Heisenberg limit, standard quantum limit. So how about if the measurement is noisy? And the answer is very strongly depends what control operations you allow in your experiment. Do you allow after the evolution to put some kind of global control that affects all the qubits or all the NV centers, or just local ones? If you allow for global ones, actually this was very surprising. We realized that you can actually ignore the measurement noise. We can prove to you there always exists a unitary that you should apply. For example, same way that the Innsbruck group was explaining, they had a global unitary that they optimized, that even a G at Z state don't feel the noise. On the other hand, if the measurement is local, if your control operations are local, so that the whole system kind of measurement plus noise is local, then you are restricted by the standard scaling, and you should actually invest in, for example, spin speed states, not in GZ states. Okay, cool, very good. So 3 more minutes. So now I would like to switch gear, and now I would like to tell you what is this problem with measuring systems continuously in time. So now we have a system. We cannot do this approach because I was talking about quantum Fisher information. We need loads of statistics. Here we have systems that you measure continuously in time, so you cannot repeat your experiment as much as you want. So here, these are these atomic sensors, and they are based typically on the measurement of Faraday rotation. So a laser goes through it, and its polarization changes depending on the angular momentum of the atoms there. And for quantum effects, actually to describe it, you get some signal, which is the angular momentum that you are interested in, but then you have some Gaussian stochastic process that describes the noise. And actually, just to say, I need to forget the quantum Fisher information because we have, for example, magnetic field that is fluctuating, so I need to go to this Bayesian estimation frameworks in which I account from the fact I need some information about actually the evolution of my field. So this is the prior evolution, how my field evolves. And we are not the first one to actually approach this problem. And what you really need here is this theory of continuous measurement that Michał mentioned, because while we are measuring some angular momentum of atoms, we are inducing back action. the atoms are decohering, and actually they are evolving. You can think of a Bloch or a generalized Bloch sphere in a nonlinear way, depending on what your trajectory is. And basically, the easiest way to solve it is goes to the linear Gaussian regime. But then, as you can see, you still have this Heisenberg scaling, which was kind of surprising. So even in discontinuous times, we get actually some kind of t to the power 3 in time and 1 over n squared in the number of atoms. Okay, so what did we do in this work? Please go to Julia Moroz-Binefa. This is the archive. We asked 2 important questions. Okay, this is all amazing, but what if you add noise? Or if you add the fluctuations of the magnetic field? Second question was, okay, if you add those and things are bad, then maybe there's a better measurement. I mean, this is basically the idea that you could maybe do some entangling measurements or nonlinear interactions that could do better. And when we provided answers, first of all, no, there exists a lower bound on sensitivity that is completely defined by noise. And secondly, actually the measurement that I showed you, this Faraday rotation, approaches it. So we are the kind of first ones to prove that the experimentalists shouldn't invest in anything else. Okay, as I'm running out of time, I just draw your attention to what is generalized. So some kind of, now the field is fluctuating, it follows some stochastic process. And then also we have these decoherence terms that we take into account. And Michał has mentioned it, actually to construct the estimator, because we have a time-changing process, we use this what's called Kalman filter. He was using Wiener filters. But these are the results. Basically, the field is fluctuating, we get some measured signal, and notice that the atoms get squeezed. They get squeezed even in infinite times. But somehow our sensitivity saturates, and it saturates to the point that defined by the fluctuations of the field. And moreover, what is the kind of, I think, nice result, we are able to prove, and it's actually quite tough maths in this ultimate limit that is defined by the field fluctuations and the strength of your noise. So I will skip the last session, which is the inference with optomechanical sensors. But let me tell you to just approach Lewis and Bartek to, if you want to learn about it. It's basically doing Bayesian inference from clicks of photons. But let me give you some conclusions. So I hope I convinced you that when you talk about quantum sensors, you should think of these 2-stage architectures. You shouldn't optimize over measurements, so you should be careful when you use these idealistic approaches from quantum metrology, like quantum Fisher information. Don't forget it, but maybe be cautious. Then, okay, we still, within these frameworks, we were able to include this impact of measurement imperfections. I encourage you to have a look at it. And then, in order to deal with sensors that operate in real time, you need to go to this Bayesian estimation theory and this theory of continuous measurements. And this is the work that we've done with Julia, that we tackle the problem of decoherence and field fluctuations. And the last part that I didn't talk about are the optomechanical sensors that you can, within Bayesian estimation, even if you go to nonlinear regime with optomechanical systems, we are able to get the information that we want. And that's all. So.
Thank you. So, question?
Thank you. So I misunderstood something because you said that in the case of noisy measurements, you can have a collective unitary that corrects the noise.
Yes.
And that's certainly not possible because I can think of a noise that just replaces the signal and produces random outcomes. So
yes,
I misunderstood.
There are some, yes. So basically, I say a non-trivial noise.
Okay.
So basically, by non-trivial, I mean that you have classical data as output, and there needs to be some information that is preserved. Okay. I mean, you can define it mathematically. You cannot.
Okay, I see.
Okay, so this stochastic map has to be non-trivial in a sense.
Right, of course. Okay.
Yes.
Great. Thank you.
Sorry, I mean, since we're close to. So you mentioned this fact that we should focus on particular measurements and not think about this fundamental quantum feature in some situations. So in your case, can you identify examples where indeed there's a gap between what you can measure and what fundamentally can be achieved if you are allowed arbitrary measurements?
Yeah, so even in this continuous measurement framework, okay, I'm restricted to what I have in slides, but okay, here I got this from our paper, and it's some kind of the Kalman filter saturates the ultimate bound graphole, but I especially chose quite strong noise. So if I decrease the noise, you need to believe me, but please ask Julia and go to our paper. This curve, which is the Kalman filter solution, will go up. So, and it will only saturate the ultimate bound, which is this weird formula at long times. So there are regimes, even in this simple model, that you should be investing in maybe potentially better measurements. But typically the systems are such that people just let them go and wait long enough. So we are kind of interested in this regime. So even in that simple system, we leave the question open.
Okay. Yes.
So I also have a question about this noisy scheme and the global unitary.
Okay.
So coming from optics, I associate like a global unitary that it needs non-classicality, I would say.
Yes, indeed, indeed.
And typically in quantum enhanced metrology, you need some special state to gain your advantage, some special measurement to gain your advantage that may be highly non-classical as well. So can you think about this, that you need even more non-classicality somehow
Okay, so I think
kill your noise?
Yeah, so I think the quickest example is maybe the Bose-Einstein condensates community, because this idea was already done. I don't have time to say it. For instance, in Bose-Einstein condensates, you drop your atoms and measure, for example, fluorescence. These are local measurements. And we know that you have some kind of Gaussian noise. The readout is imperfect. You have some Gaussian spreading of the number of atoms. And now what people typically do, they just switch on some interaction. It's called interaction readout before they measure the atoms. And this is, I think, the unitary you are looking for. I don't know if I'm answering your question. But the point is, what we are asking fundamentally is how well you can do with these unitaries. So these ideas have been done in some systems because people realized that you need to apply some, but this unitary is independent of the parameter you're trying to estimate. This is important.
Okay.
So yes.
Thank you.
Last question there. Oh, there's one more. Okay. Okay, there's, maybe we should turn on the Christian, can you
Okay,
unmute?
I can read it, but I...
Yeah, okay.
Please.
Can you hear me?
Yes, I can hear you. Thank you for the question.
Okay. So I have a bit of an off question. So if you do Faraday imaging of a BC, you talked about, briefly doing Faraday imaging. If you do Faraday imaging of a BC to determine the number of atoms in the BC, will you then change, like the back action on the BC, will that change the statistics? So like, for example, the number fluctuations. So if you want to, for example, do it, so there have been recent experiments in Aarhus, for example, where I'm from, where they use Faraday imaging to determine the number fluctuations of a Bose-Einstein condensate.
So thanks for the question. It's interesting, but I must say it's future work. So in this scheme here, we consider these hot vapors. So there you have N atoms and kind of effective spin systems, and N is some kind of a well-defined parameter. And sure, if you move to BECs, you describe them as modes, and you have excitations with mean photon number or mean atom number or excitation number. And okay, this has to be generalized, but this framework that I actually have on the slide here, the continuous measurement framework, is already also developed for continuous variable systems. But I cannot give you an answer because it will require another project. but it's interesting, so thank you.
Okay, thank you.
Okay, there's one question there, and then we should finish.
So I have a question about. I have one more question about this thing that you said that you cannot saturate this fundamental bounds sometimes.
Yes.
So in your case, your noise is collective, or does it act individually on each of the probes?
Collective.
Okay, I don't see it from here.
Actually, in the paper it's collective. So yeah, this J operator here, it's over the whole ensemble. But actually, we have bounds also for local noise, which are unpublished. So if you speak to Julia, she can write you on a piece of paper and show. But what I answered to Rafa was about collective noise. So this paper and this reference is about collective noise.
Yeah, because usually for collective noise, there are some instances where you can show that those bounds are unsaturable. Those fundamental bounds.
Okay, we have bounds that are also unsaturable for both collective and not collective. So it's not that.
Okay, really last question.
Just very short comment. In the Faraday measurements like Polchik is doing, Morgan and Mitchell, there is a regime in which they affect, not only read the state of spins, but also affect the state of
Yeah,
spins.
I used to work with Morgan, so yeah, so this is this.
Therefore, the answer to this question is that, of course, in principle, it is possible to affect.
Yes, but here the squeezing is described in terms of generalized Bloch-Paul and squeezing creating spin squeeze state. I think the question from Christian was more about BECs and quadratures.
Okay, thank you, Jan, again.
Thank you.